Hello everyone, thank you for being here. I am Weijie from the Department of Electrical and Computer Engineering at the University of Utah. It's my pleasure to present our research entitled RF Coils Characterization in Soil for Wireless Soil Sensing Applications. I will begin with the introduction. The proposed wireless power transfer through soil will then be presented. After that, I will discuss RF Coils Characterization in Soil. Then I will talk about RF power coupling through soil. I will finish with a conclusion. The world's population is expected to surpass 9 billion by 2050, which calls for increased food production, causing soil degradation. This presents a big challenge, maintaining soil health for sustainable agriculture. Therefore, we need long-term and in-situ soil health monitoring technologies. This slide shows photos of existing soil monitoring technologies, which exhibit a number of drawbacks. For example, labor-intensive for maintenance and data collection. Battery-powered system with limited operational time. These technologies are expensive and have high power consumptions with limited scalability. Future wireless soil sensing technologies need to have a number of critical features: low maintenance, wireless power and data transmission, low cost, and readily scalable. My current research work focuses on the wireless power transfer through soil. Here is our proposed wireless underground in-situ soil sensing network architecture. Ground and aerial vehicles can be used for soil sensing applications, which can provide wireless power transfer and data telemetry capability through soil. As for farmlands with tall crops, shown in the third figure, above-ground telemetry posts can be used to communicate both power and data with unmanned aerial vehicle. For soil sensing, a typical sensing depth is around 20 to 30 centimeters. Some demanding applications may require up to 1 meter depth. Typical soil parameter of interest include moisture, salinity, temperature, pH, nitrogen, phosphor, carbon contents, etc. Inductively coupled power transfer has been used for a wide range of sensing applications, such as biomedical implant, wearable sensing, industrial sensing, consumer electronics, etc. We decided to explore this technique for soil sensing applications. This diagram presents the inductively coupled wireless power transfer system, where an RF power is coupled from a primary coil L1 to a secondary coil L2 through the mutual inductance. Both coils are tuned to the same frequency. The received RF power exhibits an AC voltage swing at Vout across a low resistor R load. The AC voltage swing can be further converted into a DC voltage, for example 2.5 volts, which can energize the soil sensing system. The secondary coil L2 represents the coil buried under the ground, and the primary coil L1 is above the ground. For this work, we mainly focus on the front end, which is the inductive link. Under a proper impedance-matched condition, the voltage gain and power transfer efficiency can be expressed by these equations. From this equation, it is clear that a higher quality factor Q1 and Q2 and coupling factor K can result in higher performance. K is a function of coil's geometry and distance in between, which is typically fixed depending on the application. Q1 and Q2 depend on intrinsic loss and the surrounding median loss. Therefore, it is critical to investigate Q1 and Q2 under soil as the surrounding median. These photos show the four prototype coils. 6 cm and 12 cm diameter coils with 9 turns are built to investigate soil effect on coil's quality factor. Two types of wires are used, which are the solid copper wire and Liz wire. Both have 0.8 mm outer diameter. The Liz wire is made of 330 strands of 40 micron diameter copper wires, which has reduced intrinsic loss and higher quality factor. Here is the experimental setup for coil characterization with soil. Loamy soil collected locally is filled inside a bucket up to 10 cm. Then a prototype coil is placed inside the bucket, which has wires coming out for measurement. Additional 20 cm thick soil is placed on top of the coil. Impedance analyzer is used for characterization. Here are the 6 cm diameter coils characterization results. The first row shows the results of the solid wire coil, and the second row shows results of the Liz wire coil. In these plots, The blue curve is measured in air, green curve is measured on top of soil, and red curve is measured in soil. Let's first look at the solid white coil result in the upper section. The left plot shows 6.5 microhenry inductance. Then from the quality factor plot at the center, we can see that the maximum Q in air is 210 at 9 MHz, which reduces to 110 at 2.3 MHz when placed on soil, and further reduces to 80 at 1 MHz when buried in soil. The decrease in quality factor is due to increased equivalent series resistance due to soil loss, which dominates above 1 MHz, as shown in the right plot. As for the laser-wire coil characterization results in the lower section, the inductance value is 5.2 microhenry. The Qmax in air is 320 at 3 MHz, which reduces to 272 at 1.8 MHz on soil, and further reduces to 172 at 1 MHz when buried in soil, all of which are higher than the Qmax of the solid wire coil due to lower intrinsic loss. The equivalent series resistance plot on the right shows that soil loss caused increased equivalent series resistance above 1 MHz. Here are the 12 cm diameter coils characterization results. Like the previous slide, the first row shows results of the solid wire coil, and the second row shows the result of the laser wire coil. For the solid wire coil, the inductance value is 17.6 microhenry, as shown in the upper left plot. The quality factor plot in the center shows that Qmax in air is 270 at 4 MHz, and Qmax on soil is 130 at 1 MHz, and Qmax in soil is 95 at 0.7 MHz. The decreased quality factor is caused by increased equivalent series resistance associated with soil loss, which becomes effective above 0.7 MHz, as shown in the right plot. As for the laser wire coil with characterization results in the lower section, it has an inductance value of 16.7 microhenry. The Qmax in air is 460 at 2 MHz, which reduces to 320 at 1 MHz on soil, and further reduces to 210 at 0.7 MHz in soil. Equivalent series resistance plot on the right shows soil loss becomes effective above 0.7 MHz. The laser wire coil has higher quality factor than the solid wire coils due to lower intrinsic loss. Here are the characterization results of 6 cm diameter coils separated from soil with air gap. The air gap reduces the soil loss and results in increased quality factor. In this plot, the blue curve is measured with no gap, meaning that the coils are directly placed on top of soil. Green curve is measured with 1 cm gap, and red curve is measured with 6 cm gap. 1 cm gap can improve the quality factor significantly. For the solid wire coil shown in the upper section, the Qmax increases from 110 at 2.3 MHz to 180 at 5 MHz with 1 cm gap. For laser wire coil shown in the lower section, Qmax increases from 264 at 1.8 MHz to 310 at 2.2 MHz with 1 cm gap. From the equivalent series resistance plot on the right, it is shown that soil loss becomes effective above 1.4 MHz. Further extending the gap to 6 cm only provides diminishable improvement. Here are the characterization results of 12 cm diameter coils separated from soil with air gap. In this plot, the blue curve is measured with no gap, green curve is measured with 2.5 cm gap, and red curve is measured with 5 cm gap. As shown in the center plot in the upper section, the Qmax of solid wire coil increases from 130 at 1 MHz to 210 at 2.5 MHz with 2.5 cm gap. As for the laser wire coil in the lower section, the Qmax increases from 303 at 1 MHz to 350 at 1.6 MHz with 2.5 cm gap. The equivalent series resistance plot on the right-hand side show that the soil loss become effective above 1 MHz. Further extending the gap to 5 cm only provides diminishable improvement. This slide presents RF power coupling through soil. With a measured coupling factor at different distances shown in the left plot, the RF power transfer efficiency can be obtained. A pair of 12 cm diameter laser wire coils operating at 0.7 MHz are used. With 20 cm soil depth, the efficiency is 13%. 0.5 mW external power is required to deliver 66 microwatt RF power. The 66 microwatt corresponds to a 1 volt lumen square voltage swing across a 15 kilo ohm optimum load, which is close to the need of our intended soil sensing application. With 30 cm soil depth, the efficiency is 1.6%. Therefore, 4.6 mW external power is required to deliver 66 microwatt. The received power can be converted to a 2.5 volt DC voltage with 25 microampere driving capability. This serves an important guideline for underground wireless soil sensing network design. Here are the conclusions. Prototype coils have been characterized in loamy soil. Qmax occurs between 0.7 to 1.4 MHz, which is limited by soil loss. 1 to 2.5 cm gap between a coil and surrounding soil can improve quality factor significantly. Sufficient RF power can be coupled to enable in-situ underground wireless soil sensing network with a depth of 30 cm and beyond. Further coils optimization is expected to increase power transfer efficiency over an extended distance. Different types of soil with controlled moisture and salinity will be used to investigate system performance. We would like to acknowledge National Science Foundation for this research support. Thank you.